All right, folks, in this video lesson, we're going to look at how to solve exponential equations. So it's going to be a little bit different than how we solve linear equations. We're going to use the same ideas of the properties of equalities. So anytime you have an equation which represents an equality, ideally what it's saying is that when you have your two expressions, say I have the left side and the right side, and I throw an equal sign in between, essentially what I was saying is that these two expressions need to be equal to each other. That whatever they get as a value, as a number, that they have to be equal. So I could have, for example, like linear equations, and x plus 4 equals 6. Okay, what I'm trying to look for is what number would I plug in for x to make these two expressions equal to each other. That's known as the property of equalities. Now, what we learned about in our linear functions unit is to solve these things, to use things like simplifying, and the idea is that we're trying to solve, instead of thinking through things, to use what are called inverse operations. When we have exponential functions, however, it's going to be a little bit different on how we solve these equations, because an exponential equation, we're going to have to use the idea of what it means for two exponential expressions to be the same. Okay, so here's kind of the idea. When we look at exponential equations, we're going to have, again, two expressions, but within each expression we're going to have the thing we're trying to solve for, our variable, is going to be held within the exponent. So in terms of an exponential equation, what we're going to say is that two expressions within an exponential equation are going to be equal as long as they have the same base. Okay? And whatever they have the same base, we want to make sure that the exponents then are the same. So for example, 2 to the third power would equal 2 to the third power. So what I'm looking at is that my bases are the same and my exponents are the same. That's what it means for things to be equal. So what we're going to look at within these is how we solve different types of equations. We're going to start off with a very simple sense of when our bases are the same, and think about how do we make our exponents the same. We're going to look at then what happens when our bases are not the same. So how do we make them the same? And then lastly, we're going to look at some equations of special cases where our bases might be different values and require us to think a little bit more. So in this very first example, what we're going to look at is what happens when we have just two simple exponential expressions equal to each other, specifically when our expressions have the same base. So when I use the phrase base, anytime we have an exponential expression, you have some number raised to some power. So whatever number we have down here is called the base, and then up here is called the exponent or the power. Okay? In an exponential equation, what we're trying to figure out is that in order for two things to be equal, again, they must have the same base, and they must have the same exponent for those things to be equal. So for example, if I see 3 to the x plus 1 equals 3 to the 5th power, what I'm trying to do is I want to figure out what value of x would I plug in up here in the exponent to make these two expressions equal to each other. Now, I'm not necessarily concerned about what 3 to the 5th equals. Okay, 3 to the 5th means 3 times itself 5 times. But what I want to try and figure out is what is that value of x, in this case, x being in the exponent. So what is that value of x that would give me an exponent of 5? So the way we're going to set this up is this. As long as our bases are the same. So here, if I have a base of 3 and a base of 3 over here, what I'm trying to do is just figure out what value of x would I plug in there to make this exponent on the left side the same as the exponent on the right side. So what I'm going to do is just simply, to set this up, I'm going to ignore the bases and just simply look at the exponents. I want to know what value of x, so x plus 1, would give me 5. To solve this, I can use then inverse operations, and I would say then that x equals 4. And it's just to show you, if I did 3 times 4 plus 1, well, that's the same thing as saying 3 to the 5th. Okay, now I'm not really concerned about what 3 to the 5th means, but if I was, 3 to the 5th means 3 times itself 5 times. But the idea is this: we're solving this equation for x, but we're looking at it in terms of the exponents. All right, same thing in the second example. I have 6 equals 6 to the 2x minus 3. So again, my x, my variable, is in the exponent. So I want to know what number would I plug in there so that it would equal the left side. Okay. Now notice, because x is in the exponent, the way I'm going to think about this is just primarily looking at the exponents. On the left side, I have 6. Now, even though 6 is just a number by itself, technically there is an exponent. We are looking at just 1/6. So think of this as 6 to the first power. So what I want here is I want that 2x minus 3 on the right side to equal 1. I want to know what value of x would I plug in there so that those exponents are the same. So what I have here is a multi-step equation that I can solve. I would then add 3 to both sides. I would get 2x equals 4. And then lastly, divide both sides by 2 to get x equals 2. If I were to plug 2 into my expression, 2 times 2 minus 3, again, that's where my exponent is. That would be 4 minus 3, which equals 1. So notice that when I plug in 2 where x is, that would give me an exponent equal to 1, such that both of these expressions are equal to each other. All right, I want you to pause the video and try this next one. I got 10 to the 3x equals 10 to the 2x plus 3. Notice you have an x on both sides, but again, I want to know what value of x would I plug in to make both of those exponents equal to each other. So give this a shot, pause the video, go ahead. Solving that, I would get x equals 3. Again, I have variables on both sides, so I had to gather the variables to one side and then solve by using my inverse operations. I get x equals 3. And just to show you, on the left side, 3 times 3 would give me 9. On the right side, 2 times 3 plus 3 would give me 6 plus 3, which also equals 9. So notice that when I plug that value of x in, I'm getting 10, essentially 10 to the 9th power on both sides. It would be 10 to the 9th equals 10 to the 9th. And that's, again, what it means in terms of exponential expressions and equations for those two things to be equal. All right, these next set of examples are a little bit sassy because now we're looking at what happens when the bases are not the same. So if the bases are the same, it's just simple of trying to figure out what the exponents need to be. So we're going to take it step by step. So this first example, we're going to look at 5x equals 125. Here I have a base to some exponent. Here I have just a plain old number, okay? Then we're going to add into that, what if, the bases are different on both sides, okay? So 5x equals 125. What we're trying to think about is what value of x would you plug in there to give me 125. Now this is a problem that you can probably think through. 5 to what power? Well, if it's 5 to the first power, that's just 5. 5 to the second power would be 5 times 5. 5 to the third power, 5 times 5 times 5. And I could probably think about what value of x would equal 125. If you were to do that, you would recognize that 5 to the third power equals 125, okay? So what I'm going to do here is, because 5 to the third power equals 125, here's the way we're going to think about these problems. We're going to do what's called a change of base. Change of base means I'm going to take, if it's a number or an exponent that already has a base, what I'm going to do is I'm going to change the base so that it creates an exponential equation. So essentially what it has here is that since 125 is 5 to the third, here's what I'm looking at. 5 to the x, well, needs to equal 5 to the third. Now, based on what we did in the previous examples, notice I have x on top and 3 on top, so I want to know what value of x would I plug in there to equal 3. Well, that just tells me then right off the bat that in this case, x would need to equal 3. Again, I didn't really need to write it like this because we could have figured it out right there, that 5 to the third equals 125. But the idea is that I took a number of 125 and wrote it as an exponent. 5 to the third literally means 125. These two things are the same thing. But in order to think about this idea of exponents, I changed 125 to a base of 5 and an exponent of 3. And that's how we're going to solve these when the bases are different. So notice the second one, I have 4 to the x equals 2 to the x minus 3. So I can't do what I did in the previous slide. I can't take x and set it equal to x minus 3 because my bases are different. 4 does not equal 2. In order to do what I did in the previous examples, my bases need to be the same, okay? So they need to have the same, that's not a B, they need to have the same base. That's the key thing. So here's what I got to ask myself. I'm going to look at the bigger number, 4, okay? So 4, I'm just going to write this below it, would equal 2 to what power? And hopefully you can recognize that 2 to the second power would equal 4. So what I'm going to do is I'm going to take this number 4 and I'm going to rewrite it as an exponent. I'm going to do 2 to the second power. So instead of 4, I'm going to write 2 to the second power. And then notice there's an x on the outside. So I'm going to place that x outside the parentheses. So all I'm doing is I'm replacing that number 4 with 2 to the second power, which is the same thing as 4. Raising that to the x, then I'm going to set that equal to the other side, 2 to the x minus 3. Now, how do I simplify this? Well, what do I do normally when I see a parentheses and two things next to each other? Normally that means multiplication. So what I'm going to do is I'm going to write this as simply 2 to the 2x. And that's going to equal 2 to the x minus 3. Now what I can do is notice that I have the same base. Both of these are expressed with a base of 2. So now I can take the exponents and think to myself, okay, what value of x would I now plug in there to make the exponents the same? So I'm going to take 2x and set it equal to x minus 3, and then that gives me an equation that I would need to solve. So in this case, I got to, again, gather my variables to one side. So I would get 1x equals negative 3, and then that tells me that my answer here should be x equals, oops, not 3, but x should equal, in this case, negative 3. If I were to take this number negative 3 and plug it all the way back in at the beginning, so for example, if I did 4 to the negative third power, that's going to give me, I'm going to write it as a fraction, 1 over, not 16, God bless it, 1 over 64. If I take negative 3 and plug it into the other side, 2 to the negative 3 minus 3, that's the same thing as saying 2 to the negative 6th. If I were to plug that into my calculator, I'm also going to get 1 over 64. So what ends up happening is I found the value of x that makes both of those things true in the end. It's kind of like saying when x was equal to 3 over here, that both sides would give me 125. What I had to do here was change the base so that the bases were the same. All right, last example here in blue. This one's going to be extra sassy but also extra classy. Notice again, I don't have the same base. I have 9 and 27. So what I'm going to have to do is change the base. Now what we did before is we took the larger base 4 and tried to express it in terms of the smaller base 2. 2 to the second power gave me 4. So I'm going to try and do the same thing, 27. Can I break 27 down into 9 to some power? So if we think about this, okay, 9 to the first power is 9. 9 to the second power is 81. It means 9 times 9 is 81. So notice that I'm not getting 27. And that is because 9 cannot be expressed using an exponent to get to 27. So in this problem, what I'm going to have to do is I'm going to have to think about, is there a way to change not one base, but both bases? Do 9 and 27 have a base in common? Now, if we think of 9 you might be able to recognize as 3 to the second power. 3 times 3 gives me 9. So can I express 27 as 3 to some power? And you can. 27 is 3 to the third power. So I'm expressing 9 as 3 to the second power, and that is 3 to the third power. So in this equation, what I'm going to do is instead of the 9, I'm going to write 3 to the second power. Leave my exponent of x plus 2. And then on the right side, instead of 27, I'm going to write 3 to the third power, and then just put my x. Now what I'm going to do is try and simplify this. So to simplify, I'm going to leave my base of 3, but notice here I have 2 and then parentheses x plus 2. So what that means is I'm going to have to take this 2 and distribute it like I would normally do when I see parentheses. And that would simplify then to 2x plus 4. And on the right side, I'm going to do the same thing. I have 3 and x inside or next to each other in parentheses. So that's going to be the base of 3, and then that's going to become 3x on top. Notice now that the bases are the same. So that the bases are the same, I can now take my exponents and think about, okay, what value of x would I plug in into the exponents to make those exponents also equal? So then I'm going to take the exponents, 2x plus 4, and I'm going to set up another equation to think about how they're equal. So to solve this, what I'm going to do is subtract 2x from both sides. I'm going to get 4 equals 1x, which just simply tells me that x is going to equal 4. If, again, I were to plug this in, if I were to take 4 and plug it all the way back into the front, or to the very beginning, I would get 9 to the 4 plus 2 power. 9 to the 4 plus 2 is like saying 9 to the 6 power, which is going to give you a pretty big number. It's going to be 531,000 and then 441. And if I did that same thing, if I took 27 and run out of space here, if I did 27 to the 4th power, I get 531,441. So I figured out the value of x in the end that would give both of those things, or make both of those expressions equal to each other. So what I did is I just used a property of equality that said the bases need to be the same as well as the exponents need to be the same. And I just worked my problem that way. All right, this last one is going to be what happens when we have a base that is a fraction. So remember we talked about that it is possible with exponential decay that my multiplier b could be between 0 and 1, which means that b is going to be a fraction or potentially a decimal. So we're going to look at what happens when we have things written as a fraction. We're going to use the same property that we did in the previous examples, that in order to solve these, we're going to try and make the bases look the same, and we're going to try and make then the exponents look the same to try and think about what that value at x would be. Because again, in this simple equation, I could just plug in random numbers and try and figure out what value would give me 4. All right, so what we're going to do first is when I am given a base that is a fraction, what I'm going to first do is I'm going to try and take that fraction and turn it into a whole number. Now the way we're going to do that is this. 1/2, we're going to try and change that into a base of 2, okay? And we're going to do what's called an inverse. An inverse means I'm going to take 1/2 and I'm going to flip that fraction and make that into 2. But when I do an inverse is always going to have an exponent of -1. So if I have 1/2, that'd be 2 to the -1st power. In the next example where I see 1 over 64, let me just rewrite this. So 1 over 64 would equal 64 to the -1st power. So we're going to start off by doing that. Anytime I see a fraction, we're going to do the inverse by writing it with an exponent of -1. So I'm going to take this 1/2 and I'm going to write this as 2 to the -1st, and then I have the x on the outside. Now, notice here that I have then a base of 2. So just like we did before, here you're given 4. So what we want to do is we want to make sure the bases are the same. So 2 to what power would give me 4? Hopefully you recognize it's 2 to the 2nd power. So I wrote 4 as 2 to the 2nd power. Now to simplify this again, notice I have -1 because of that inverse in x. So I can simplify this and write it as 2 to the -1x power, and that's going to equal then 2 to the 2nd power. So notice how my bases are the same. Both my bases are 2. So now I want to figure out what value of x would I plug in there to make my exponents the same. So I'm going to do -1x, set it equal to 2. Then simply by dividing both sides by -1, I would get x equals -2. And that would be my answer. If you were to plug in, for example, the very beginning, if I were to do 1/2 to the -2nd power, that should give me 4. Okay? But what I did is I first took the inverse, I then changed the bases so they were equal, and then used my exponents to solve the problem. So we're going to do the same thing in this next one. We have 4 to the x plus 1. What I already said is we're going to take that 1 over 64 and write it as 64 to the -1st. That is what's called here an inverse. So an inverse, we're always going to have some base to the -1st power. Okay? All right, now what we're going to do is try and change the base. So can I express, and I have the larger number 64, can I express 64 as 4 to some power? 4 to the 1st power, for example, would be 4. 4 to the 2nd power would be 16. 4 to the 3rd power would be 64. Okay, So I'm going to re-express 64 as 4 to the third power. But remember we said we already have that -1. So I'm going to keep that -1 there. And then I'm going to bring down the 4 to the x plus 1. So when I change my base again, I'm always going to put that in parentheses and leave the exponent that's there on the outside. So now, to simplify, I have 4 to the x plus 1 equals, and I'm going to keep my base of 4, and now because these two are separated by parentheses, I'm going to multiply them, which would give me -3. Now that my bases are the same, I can try and think about what value of x would I plug in to give me -3 as an end result. So I'm going to take x plus 1 and just set it equal to -3. I'm then going to subtract 1 from both sides, and I'd get x equals -4, and there's my final answer. What that then tells me is if I were to plug in -4 up here, so if I did 4 to the -4 plus 1 power, that'd be 4 to the -3rd power, which is the same as 1 over 64. So again, we're finding the value of x that would make these equations true, but we're using the property of equalities for exponential equations that says in an exponential equation, as long as the base are the same, then the exponents are the same. All right, so this is a little bit sassier than solving regular equations. So again, jot down any questions you might have, bring those to class, and we'll see you guys next time.